AI in political science or AI in social science. It's a very broad topic, and I didn't try to actually give an overview of that, but I'm just going to talk about the latest free research in AI in political science that we've done. So it's done with all those people around, as well as data decision CRC team, which related to the first topic. So we extracted events from newspapers related to civil war in Afghanistan. This is current research, this is past research. Developing methodology for forecasting, used to forecast genocide onsets, and investigating military interventions on the lasting piece, whether interventions have positive or negative effects on the lasting piece using machine learning and network analysis. So moving to the first one, the purpose of this topic of this research was to give an analyst some kind of tool and models to monitor the newspapers and quickly get the events of interest. Newspapers are different, New York Times, The Guardian, as well as local papers, local to Afghanistan, obviously. And here is this example, Taliban attacked bus with tourists and resulted in some casualties. So what we've done and what we developed was something with human-assisted extractional events, so human-in-the-loop thing here. So this interface is used by end-user, hopefully analysts. Analyst gets the article displayed, and events are displayed where actors of event and target of event. Actors are yellow, targets are green, and the action, what actors actually does, is in red. So this is done by incrementally. So the article appears one at a time. The analyst can choose an article and so on. And during that time, analysts may change or may accept current event as valid or may change. When the change is done, a new natural language processing pattern is developed and stored and used in future. Here is ontology, which is used to identify names, places, it's especially useful when different spellings are used in foreign languages. And here is a panel. Here is a panel of ontology that also can be changed by the users. And we found that event coding assistant, this is what we call this interface, reduces annotators coding time due to reuse of automatically generated patterns. So there are many patterns generalized to be used. This is a brief view of the first topic. Moving to the next one, which is current topic in progress. Forecasting genocide events. Here is developing methodology for this forecasting. And the reason why developing methodology, I'll say in a minute. Just forecasting genocide events. Genocide events are important because they affect a lot of lives and they happen in a country. Luckily, there are not too many, but this also creates a problem, methodological problem, how to approach this kind of problems. So we wanted to address this methodological issue one at a time or together. And the purpose of this is to actually get the models to be actually useful for analysts, possibly being useful in some applications. So here are the issues. Numerical data with lots of missing values here. Data highly imbalanced, so we have only this many events that we want to forecast, but this many irrelevant other events or irrelevant data points. What's currently being used in the literature, in social science and other literature is the training procedure that is based on split and cross-validation. We found that it's not very practical in these settings because we're dealing with incrementally acquiring year by year. So analysts looking at 1 year at a time, and the data is changing. Maybe potentially dealing with constant drift here. So the metrics are also not very practical that currently being used. They are good for research, perhaps to compare models, but some of them overestimate, some underestimate the results. So, and we address these issues by data imputation and upsampling. There are many algorithms available for both of them. We try to incorporate them into a loop so that they are cited automatically in the process of generating events. And here, the training procedure, we use multiple windows, which is quite complex, but hopefully in the future paper, more details on that. And for metrics, we choose mean average precision over K, where K is number of events shown to the user. This metric is very popular and widely used in recommender systems. So the question is that we also address is how many predictions to show to the user. Okay, this is possibly kind of recommender system. If too many, the user will not be able to choose or view them. If too little, important events may be missing. We found an optimal point by optimizing some of this mathematically and using trained models. Okay, so this is for the second topic. Moving to the next one, which is analysis of networks to forecast what kind of effects military interventions have on lasting peace. This is topic done by our honor student, currently in progress again, Nicholas Bosworth. And we again encounter here missing values, imbalanced data, problem of metric selection, and so on. So currently the student decided to use two models, stochastic act-oriented model, SIOM, which initial results have produced some coefficients which can tell which variable and which factor influenced the prediction more or less, and in what way, negative or positive way. Negative not necessarily meaning bad way, but just the coefficient. And temporal exponential random graphic model, where we're hoping to predict new intervention networks. So this approach is, instead of predicting events, we're trying to predict the whole network of international military interventions. And finally, hopefully I can present this network. How are we going? Okay, here we go. So there are not too many of interventions, but sometimes you can see some clusters. So the points are countries or multiple countries, and the yellow one, which are affected targets, and the relations are interventions. So that's how it roughly goes. Okay, and that's all about social science, AI in social science. Thank you very much for your attention. Very brief. And yeah, any questions, please post, ask. Thank you.
Thank you very much. Well, in the interest of time, we're gonna move on. One thing that UNSW is famous for is its robots and playing games, and especially robots playing games. So all the rest of the talks, I think, for the rest of this hour are involved with robots playing games. We're going to begin with one of our research fellows, Eduardo, who's going to tell us about robots playing Ultimatum. Eduardo, over to you.
Okay, now I'm on mute. So I'm sharing my screen.
We can hear you.
Can you hear me?
Yeah, we can hear you. You have the
Perfect.
screen.
Okay, can you see my slide?
Yeah.
Can you see my slides?
Yep, we can see your slides.
Okay, perfect. Well, thank you so much for having me here. Today I will present my work related to reciprocity in human-robot interaction that relies fully in decision games, which are a particular technique of game theory. So this work, it's applied in human-robot interaction, which is the field of study trying to understand, design, and evaluate robotic systems for use by or with humans, which is a very general, broad definition of this field. And you know, this is the kind of social robot that we have at the moment. Mainly, most of these robots are for research, and more recently, few of the robots that you can find in the bottom column are more commercial products, which have been the first attempts to bring the robots to domestic environments. Some of the robots are quite popular, like Now Robot, which is probably the most popular research platform. And some others are more commercially viable, like Sphero or Roomba. But when we talk about the robots, what we notice is there are different philosophies in designing robots. For instance, some of them don't try to avoid their uncanny valley, and they have this very humanistic appearance. But more new recent developments, we have more designed embodiments in a minimalistic way. However, what we notice is that you know, whatever robots we will use in the future, these robots will have identical embodiments, and what will make the big difference among them is the behavior that they display toward humans, and that's what makes sense and justify this kind of research. In behavioral terms, in robots, reciprocity and likability will be very important factors to consider once that we design the behavior and the AI required to interact in social domains with humans. For reciprocity, we have the normal reciprocity as a main definition supporting this work, proposed by Goldner in 1960, which is very well known in all the cultures. It's very common in all the religions, and it's pretty much what you do to me, I will do to you for good or for bad. Likability is a little bit more difficult to define. It's a very complex variable that is associated with friendly, cooperative, and post-social behaviors. And this one is very interesting because we discovered this one in our second study, and definitely it's one thing that we believe will make a big differentiation among the robots once that they are more available for the general population. So the research questions that we have when I start to develop this project about reciprocity in human-robot interaction is first thing, does reciprocity appears in human-robot interaction? If so, to what extent do humans reciprocate towards robots? Secondly, to what extent can robots use reciprocation for their own benefit? Because that could be interesting in terms of using robots as a persuasive machines or as a manipulative machines. And then also, what are the most beneficial and likable reciprocal strategies between humans and robots? So to explore these questions, I have developed as a first out of these 3 different papers along the years. The first one was published in 2016, and the last one, which is the one that I will mainly talk in this presentation, was presented in June 2020. So to explore this topic about reciprocity, I mainly use game theory, as I said before, and mainly use Prisoner's Dilemma game, Ultimatum's game, Rock, Paper, Scissors game, and a novel version of Ultimatum's game that I call alternate repeated Ultimatum game, which is also the one that I will describe in this presentation. So if I can show you the videos about how these experiments were running along the sessions. So essentially the first experiment relied mainly in Prisoner's Dilemma, which is this metaphor about 2 prisoners who should cooperate of the fact when they confess towards the people. So If they cooperate, they minimize the penalty that they receive going to the jail. If one of them defects, well, this guy goes to jail and the other one stays for free. And if both of them defect, they also have a different outcome compared to the first one. In the second one, the robot play rock, paper, scissors. And in the bribing condition, we'll try to persuade the robot to the human to obtain a favor, the robot cheats, but intentionally loses in certain rounds, providing the human with 25% more income along the game, expecting a reciprocation of that favor. Interesting things that we found here is that, first thing, people tend to reciprocate in similar fashion towards robots compared with humans, but definitely they cooperate more with humans. Secondly, in the negative side of reciprocity, people don't report the bribe that the robot displays when they are in the experimental session. And also they don't reciprocate this unrequested reciprocation that the robot performs towards them. So essentially, the strategies keep robot honest and straightforward. However, something that we found is that because the unexpected behavior of the briber robot, people rate the robot in the Godspeed scale as a very likable. And that gives us a cue to try to investigate in this new experiment what kind of strategies make the robots more likable. So for this thing, we designed 4 different behaviors that depends on the robot's decision, if the robots reciprocate or no, when they are playing Ultimatum's game, or and the offer in financial terms that the robot offers to the person. So if the person offers little money, the robot can offer little money in the next round. Or when it's inverse reciprocal offer, people can offer little money and the robot reciprocates with a high offer. So we had 38 participants, all in the 4 conditions. So we have 152 sessions to analyze. And these are the variables that we explore, like robot likability, the reciprocal decisions of the participants, the offer, the reciprocal offer from the participant, and the profit that they obtain during the game. So I will skip all the statistics and all the boring stuff, and I will go directly to show how the sessions were performed, and then what are the main conclusions that we have from this experiment. So the robot and the participant interact verbally, and they have these cards that can be identified by the vision system embedded in the now robot. And essentially they run this runs for 20 times, and the person and the robot use the words yes, not to accept or refuse the offers and distribute the money that is part of the game. So essentially this is a sample of the round, and this procedure happens after this round. The people was able to evaluate the characteristics of the robot. So what we learned from this experiment is that the general robots are scored higher when humans start interaction, and also reciprocal robots score higher when the robots start interaction. However, when they rank the robots, it's a different story. Reciprocal robots are highly ranked compared with generous robots, the robots that during the interaction offer a lot of money, which is a big incentive and also has an impact in the profit of the participants. And that we believe has an impact in how they score the robots. However, because the reciprocal strategy is more understandable, in the other scale, they also rank it very highly. Also, we noticed that the pattern suggested by the norm of reciprocity is also applicable in this scenario. So the participants' decisions are influenced by the robot decisions during the game. And that experiment confirms that the norm of reciprocity still applies and it's in line with the previous studies that we developed. And this investigation related to reciprocity, I think that has a lot of impact in future collaboration, persuasion, corruption, and trust studies in HRI. And I know that because the citations that we have around almost 80 citations are related to these topics. So if you're curious about this topic, let me know, and I provide you a copy of the manuscript. And finally, that also leads me to another research domain, which is robot games. Now I'm interested in the games as a main instrument for meaningful interactions with robots. I reckon serious games and fun games are an ideal way to explore what kind of cognitive, intellectual, and emotional benefits offers can offer us. So if you're interested, please give me a shout in Twitter to my personal account or to the robot games group that I recently created in Twitter. Yeah, and that's all. Thank you so much.
Thank you, Eduardo. So I'm going to, again, take my privilege, ask a quick question before we switch to our next speaker, which is, so is the high-level takeaway that if you're building a robot, a social robot, you should make its behaviors simple, direct, and tit for tat?
Yeah, that's correct. That is probably the most efficient way, but a little bit of unexpected behavior is also appreciated by the users when it's not deviated too much from the main behavior, which is also a technique that is very often used in websites and even supermarkets. We humans enjoy a little bit of change, but not too much change. We want to understand these behavioral patterns when we interact with machines. I think so.
Thank you very much. Well, I mean, as we began this morning at the lunchtime with Marianne's talk, which reminded us of the importance of human, it's nice to continue that theme here. We're now going to move over to one of my colleagues, Michael Thielscher, another professor of AI in the school, who's going to tell us about some general gameplay. Michael, you should have the stage.
Thank you very much. Let me just share my screen. Can you confirm that you can see my slides?
We can hear you fine.
And see the slides?
Yep, we can see the slides.
Okay, excellent. Well, thanks everyone for sticking around for the last session. Under normal conditions, I would now say that I'm one of the last speakers between you and the drinks that we would have after this session. Next year we can have that. So I'm going to continue this topic on game playing, but before I'm getting to game playing per se, let me give a very brief background on where this fits into, and that is an attempt to build so-called general problem-solving AI systems. When we look at Wikipedia, for example, the standard definition of intelligence says that it is the ability to perceive information and then to retain this information as knowledge to be applied towards adaptive behaviors within an environment. And I'm stressing this adaptive here because this is in particular what I'm interested in. I think this is one of the, or maybe the key issue of intelligence, that we humans can adapt to new tasks and new environments. And this is what we're also interested in when we want to build systems under the artificial general intelligence topics. Artificial general intelligence is meant to enable systems to understand new tasks and adapt to these new tasks without human intervention. This means that we are interested in building so-called general problem-solving systems, which by my definition is a system that can, that can take a problem description as an input and then solve new problems, as we've said before, without human intervention. The reason why I'm particularly interested in this is for the following two theses. First of all, I believe that designing general problem-solving systems does pave the way towards artificial general intelligence. That is, systems that do have the capability to adapt without human intervention to new environments and new tasks. And what turned out to be almost always the case when you want to build a general problem-solving system, including a robot, then that does require the systematic integration of different AI methods. And the particular example that I'm going to show you next is I'm showing that this is really necessary. now the more specific topic, as an example of a general problem-solving system, I'm interested in general game-playing systems. The context of this is that most AI programs, in particular game-playing programs, for specific games have been used algorithms that cannot be transferred to a different context. And two very prominent examples is the computer that was able in the late 90s of the past century to beat the then world chess champion, which used a particular method to play chess, which was very, very different from the method that was used about 20 years later by a system by Google that was able to beat one of the best Go players. These two systems used very different methods, and they couldn't simply be applied from one game to another game. In contrast to these very specific algorithms, general game-playing system as an instance of a general problem-solving system is a system that understands descriptions of new games, games that the system hasn't seen before, and learns to play these games effectively without human intervention. And on the next 3 slides, I will show you the latest approach that we took in order to build a general game-playing system. In a nutshell, what I'm going to show you is that you can obtain a general game-playing system by combining what has been used here. The system known as AlphaGo, which a year later was generalized to AlphaZero, that was able to not only play Go at a superhuman level, but was also able from scratch to learn to play 2 other board games, namely chess and shogi. And that system was called AlphaZero. And then what we built was a general game player where we basically combined everything that underlies AlphaZero and combined this with a very different method, AI method, that comes from knowledge representation and reasoning. Now, what do we need from the knowledge representation and reasoning perspective is that when we want to describe new games to a general game playing system, we have to tell the system what the rules of a game are. And for this purpose, what has always been used in this context for almost 20 years now is the so-called game description language, which I'm not going to introduce in detail. I'm just going to show you an example on how you can specify the rules of a very well-known game, chess. This is a symbolic knowledge representation language, which allows you to, as we can see here in the first line, describe the initial position. Standard position in chess would be that one of the board cells, cell A1, contains a white rook, and then you list all the 32 pieces that you have in initial chess position. H8 contains a black rook. This is the initial position. Then you have to tell the system what are possible legal moves in a game. For instance, a special move in chess is to castle in either the king side or the queen side direction. One of the conditions for this would be that the white king is still in its home square, E1, and there are a few other conditions that you list here. You also tell systems what the effects of specific moves are, and that would be, for instance, if white castles to the king side, the white king would end up in cell G1. And then there are further rules. Of course, you have to explain to a system what checkmate means, and that implies that you have won a game. But in a language like this, you can specify games like chess with a few hundred lines of code. And in fact, you can specify many, many other, in a sense, all games with the help of a high-level knowledge representation language like this. Now we have combined this knowledge representation technique with a very different technique, which underlies AlphaZero, that combines both search and learning. And again, just to give a very crude overview, the search and learning in AlphaZero was based on 2 methods. The search method, which uses, and this is for the expert, the so-called Monte Carlo tree search to perform a self-play. MCTS here stands for Monte Carlo tree search. The way this self-play has been guided was with the help of a self-learning deep neural network. And this deep neural network, in turn, was trained with the help of the results of every single round of self-play. Self-play resulted in a specific winner, and this winner was then being used and this information in order to update the neural network, thereby learning to play better in the next round in every state that the system went through in this self-play. So this result was used to improve the neural network. We then combined the knowledge representation side as one aspect of the general architecture of what we called general game playing zero as a further development of AlphaZero. So we did have the game description language input here and some form of symbolic knowledge representation processing, also known as reasoning. And this was then combined with a neural network that we used for self-learning in the exact same way and for search as was done in AlphaZero, with the result that this neural network was able to predict an expected reward and move probabilities, qualities of moves for every player in the game. The generalizations that we achieved by doing this was, if we compare this to AlphaZero, AlphaZero was actually tested on the 3 games only that I have explained at the beginning, and that it was designed for. It requires that a game has only 2 players. That's a so-called zero-sum game. It is symmetric, has to be turn-based, and AlphaZero also relied on a board-like structure. Plus, AlphaZero was using a handcrafted neural network architecture for each individual game that they tested. In general game playing zero, we overcame all of these limitations. We were able to build a system that can learn any game that can be described in this knowledge representation language, GDL, as input. And we were also able to play cooperative games, so not necessarily zero-sum games, and asymmetric games in general by generalizing the neural network to have an output layer for each player. And with this, I'm reaching the summary slide already. What we have built in this work that I very briefly presented was a general AI system that did combine different methods, in particular, in this case, knowledge representation and reasoning on the symbolic level, and then search and learning deep neural network on the sub-symbolic level. If you're interested in reading more about general game playing, I can also advertise a book that contains some basic techniques that can be used for general game playing systems. And I should conclude with thanking in particular my student Adrian, because that was mostly his work that I was presenting here based on his thesis from last year. I should also thank my 2 current students, Cameron and Kevin, who are continuing Adrian's work with further investigations into building general game playing systems that do combine knowledge representation and reasoning with AlphaZero deep learning techniques. And I should also thank my co-authors and collaborators, Ajit, Alvaro, and Jiran from Auckland University of Technology, with whom I also work in this area. Thank you very much for your attention. And I think I can then pass on to Abdallah, who's going to continue in this, along this direction with more work on generic systems that can be adapted to new problems.
Thank you, Michael. Thank you very much. I mean, it's fantastic to see work that combines together the traditional knowledge representational approaches with deep learning. Many people believe that is the future for making significant progress, certainly if we're going to go towards artificial general intelligence. I guess general game playing is Turing complete, so literally you're being able to play anything.
Well, what we have at the moment is restricted to the game description language, and there are still a few limitations that we are looking into relaxing. In particular, we can't play games like poker because so far everything requires symmetric and perfect information. But this is something that we can lift And we will also be looking into applying techniques like this to the so-called general video game playing competition, where we go from these more symbolic discrete games to, as the name suggests, video games, and see what we can do there with similar techniques.
Great. Thank you very much, Michael. We're going to move, as Michael said, onto one of our amazing DECRA fellows, Abdallah. Over to you, Abdallah. Let's see you.
Can you hear me now?
Yeah, we can hear you and we can see your screen.
Awesome. So yeah, today I want to go a bit further than Michael did by telling you about how to encode problems in this format that are suitable for the generic problem solvers. And I will start with a challenge that Toby offered the AI community back in 2003. Toby asked us solver capable of solving the game of Connect 4. Now we have to keep in mind that that game of Connect 4 was solved already by specialized algorithm as early as 1988. And so 15 years later, the generic problem solvers were not yet capable of that. And that's the start of this work. So let us take a step back and look at how computers can help solve problems. So we've got the real world, the math world, where everything is nice and defined, and then the computers that can help us. The simplest way of solving a problem from the real world is to translate it into the math world, and then to design a specialized algorithm such that the computer world can help us solve the problem. Now, with a general problem-solving approach, we introduce a middle thing, that generic solver, or the general problem solver that Michael was talking about. And now we are not writing a specialized algorithm anymore. We are writing a specialized encoding of the problem that we want to solve. This would be writing the rules of chess in the game description language that Michael was referring to. But there are many ways of writing this file that contains the rules of chess. And so we could have many different encodings for the same problem. I will try to convince you today that choosing an appropriate encoding can be quite beneficial and matters. So to do that, I will look at 5x5 tic-tac-toe, where the objective is to put your pieces so as to reach an L shape, like this or that, this or that. So the rules of the game are very simple. Players take turn placing stones of their color, and here black has a threat. Maybe black can play this 9th move unless white blocks. And from here, could we tell who's going to win this game? Well, I don't know, just looking at that, it's a bit difficult for me, but we can ask a generic problem solver. And based on the work that we did this year, now generic solvers are capable of answering this question, in this case in 18 seconds, and tell us, yes, black can force to win 11 moves. How to do it? Well, start like this, and the best move for white is that, followed up by the sequence of moves, and eventually black obtains an L like this, and there was nothing that white could have done to delay it further. That nothing that white could do is one of the tricky bits to guarantee. Anyway, to obtain this result, that black can force a win in 11 moves within 18 seconds, two things are collaborating. The encoding of the problem, how do we describe the rules of 5x5 tic-tac-toe, and the general problem solver that could be using AlphaZero type of techniques or some other ones. And I want to compare the contributions of these two parts in that specific type of problem. So we looked at some 4x4 tic-tac-toe positions, 96 benchmark positions of a varied nature that were proposed by some Japanese researchers back in 2016. So there's one way of describing these positions, the rules of tic-tac-toe that the Japanese people have proposed, and there's our new approach for doing it. And then we compared also different general problem solver technology, one from Germany called Cake, 2 from Austria, 1 from Portugal. And then we measure the time needed by a solver to solve a specific encoding and tell us if the first pair could win or not. Sum the total time, and we see the right column, these measures. What we can see here, obviously, is that depending on the solver, the total time is different. But we can also see that depending on the encoding, the time required is different. And with our encoding, we get a 20-fold improvement using the same generic solving. So writing the rules of your domain in a smart way or in a better way can definitely improve the performance. So that's my collaborator, Valentin, and a takeaway message from the first half of this talk. The performance when you're trying to solve a problem using a generic solver depends both on the solver quality and on the encoding quality. You can see here my collaborator, Valentin, playing the game of hex. The game of hex is quite popular among mathematicians. And I want to tell you a bit more about how results about hex are progressing. So back in 2002, a Canadian researcher, Yang, has published a paper showing how to win, how to play perfectly the game of hex on a board 7x7. This paper was all done by hand, in a sense. It's a mathematical approach. There's no computers involved. So it's a hand verification of the result. And then 8 years later, we got computers that could do that and better. And we have that paper solving hex beyond humans, where a very specialized computer hex solver could now solve even larger hex openings. In my work with Valentin, we've started using generic solvers, not automated hex solvers, to solve hex. And what do we get? We get that we can solve 5x5 positions. And so we could have named our paper Solving of Positional Games Beyond Trivial. That's not the actual title, but that's the idea. Generic solvers are at a handicap because they cannot use that specialized knowledge that the automated hex solver can, but we're getting there. We went from solving 2x2 to 5x5, and that's a step, and with more work, we'll get to even more realistic sizes. Now, along that line of how do we get to realistic sizes, I want to tell you about the second part of the work I present today, which has to do with a very real-world based application, which is peer review for small-scale farmers. And here we have some pictures of an association in Morocco, in North Africa, called Agroecologie Maroc, and it's a small farmer market. And what's the problem here? Well, we want to have products that are farmed sustainably and that are organic and fair trade and everything. And you probably recognize many of these labels. The issue with these third-party certification labels is that they're very expensive, which makes them unaffordable for small-scale producers, especially in developing countries. And there is an alternative or complementary approach called second-party certification that is growing in popularity, where in these so-called participatory guarantee systems, producers and volunteers band together to form an association. And as the association, they will review the production site and decide if a production site gets a label or not. The benefits is that it's much cheaper. It increases the consumer trust in the products that you will consume. And the producers can share knowledge and tips. And that can also show other producers that sustainable farming practices are feasible. What are the main challenges here? Avoiding free riders. So producers who participate get the labels but are not contributing back. And the main thing is that setting up and organizing are very time consuming. So let me run you through an example and tell you how this thing works. So every year, for one association, every year you want to group the participants in committees and assign them to production site. The committees will inspect the sites, write reports, and the sites that do well, they get the label, which will guarantee that they're doing things in the proper way. So for instance, we may have these 7 farmers from Albert to Fanny and 2 volunteer consumers, and we now need to group them and tell them who is going to review which site. So that would be one way of doing it. Gaston is going to be reviewing Albert's production site, along Bertrand is also reviewing Albert's production site. That's the objective. That's what we focused on in this work, helping the farmers by helping them group participants in committees and assign them to production sites. So why is this grouping difficult? Well, the reason is that there are many constraints. For instance, if A is on the committee reviewing B, then we cannot have B in the committee reviewing A for conflict of interest reasons. We also want to have a fair spread of the workload. Each producer should be reviewing the same number of sites. Some temporal guarantees that the committee from 1 year should follow up on the next year, etc. So coming up every year with an allocation or with an assignment that satisfies all these constraints takes the organizers a while. And they asked us if we could use computer science techniques to help them. And that's what we did. That we developed a mathematical formulation of the problem, an encoding for it, tested on the data, published a paper. So that's what it is for us. We have a real world problem and we get nice theory and results about it. Now, we also tried to help them back. So we suggested an assignment for the year 2020 and got feedback on it, why they were not so happy. Because someone was assigned only follow-ups, she was bored. Someone was in a committee, but he never refused action. So we had to change our encoding and add new rules, which we did. And then they were happy. With the second assignment, we suggested them, they were happy. And that's how some farmers in Rabat in Morocco have organized their label allocation based on the software that we created, which was itself an encoding fed to a general problem solver that we did not create. So we just created the encoding. So what's the takeaway message here? That generic solvers can already solve some real life problem, that this approach is robust, flexible. If the constraints change, they hadn't explained to you properly how things work, you can adapt it, and that's cheap. My collaborators were Nathanael, Sylvain, and Nicolas. So what's next with this Helping Farmers project? Well, we will continue our pilot study with Moroccans, and we have received expressions of interest from groups in other African countries like Benin and Tanzania, and there's also an association in France who wants to get involved. And we will be co-organizing a workshop called How Can Digital Tools Support PGS Development and Functioning at the Organic World Congress, which is not an academic conference, it's really about farming and the organic world that I know very little about, but because of that generic solving approach, I can help and contribute to that. Thank you all for your attention.
Thank you, Abdallah. Let me ask you a quick question. If I understand right, this means we're helping farmers in Africa with SAT solvers.
Sorry, could you please repeat your question?
Am I understanding this right? We're helping farmers in Africa with SAT solvers.
Essentially, yes.
I would never have imagined in my wildest dreams that the SAT solvers, abstract SAT solvers I've worked on 20 years ago would be used to help farmers in Africa. This is wonderfully inspiring to hear the unexpected applications.
Yeah. So in that case, we're using ANSYS SAT programming solvers. It's the same thing.
What's a SAT solving? But it's wonderful to hear such practical applications to all these.
Yeah, it's great.
Great. Well, we're really, I'm afraid we're going to run 10, 15 minutes late, but we're going to switch now to the final talk. Another one of our really inspiring PhD students. And staying with the theme of, I believe, with combining the symbolic and the neural. So Jingying, let's. So Caroline, can we come over to you?
Can you hear me?
Yeah, I think, yes, I can see you. I can see your background. I can see your screen.
Yes. Can you see my PC?
If you turn your camera on, we can see you talk as well.
You can see me.
We can't see your camera. You just see your slides.
Because I share my screen. Now you can see me, right?
Now we can see you. Wonderful.
Yeah. Yeah.
Over to you.
Yeah, okay. I'm going to share my screen now.
Yep.
My speech topic is a hybrid neural symbolic reasoning model for visual question answering. My name is Jingying Gao. I'm a second year PhD student in the Computer Science and Engineering School. Aim is to use a hybrid symbolic neural reasoning model to improve visual question answering reasoning capability. We integrate symbolic knowledge representation and logic reasoning with neural networks to enable agents such as robots to answer complicated questions and provide answers through reasoning. The current robots lack complicated reasoning capabilities. For example, Molly is the world's first fully automated and intelligent cooking robot. It learns recipes, cooks them, and dresses up after itself. It can mimic the actions of a master chef precisely, cooking a variety of delicious dishes. However, it still has some important flaws. The current robots lack visual and language reasoning systems. They are not able to infer actions through visual question understanding, not able to discern the executed results. For example, whether the correct ingredients have been placed instead of copying the movements mindlessly. Now imagine you have a new cooking robot called Ada working with you in an Italian restaurant. In the natural environment, you talk with your robot Ada. Hi Ada, can you help me to prepare the recipes and ingredients of spicy noodle? Can your robot Ada prepare the pepper or chili correctly? Hi Ada, can you help me to get the different appliances for fried eggs or boiled eggs? Can Ada bring you a pan or pot accordingly? Hi Ada, can you use a similar ingredient inside if you don't have the right one? To let the robots answer these questions and execute the task, we need complicated reasoning by joined visual and natural language understanding. In the robot's eyes, this world is a dynamic video. Comparing with human, when humans look at this video shown here, not only can we answer questions to describe the objects or events that happen, but we can also reason about the causal structure behind the events, making predictions about the future and imagine unobserved counterfactual scenarios. This naturally leads us to the question, given a video asks a question, can machines such as robots perform reasoning tasks, such as description logic reasoning tasks, and provide answers which they might not be able to see in the video directly in the way that humans are capable of. Therefore, we created a hybrid symbolic neural reasoning model for robots. And this robotics mind has a hybrid neural reasoning model. And this model has two inputs. One is what the robot sees from this dynamic world. We call it robotics language understanding. And the other one is what the robot sees from this. One is the robot from the robot here from the people. We call it the robotics language understanding. The other one is what the robot sees from this dynamic world. We call it robotics visual understanding. And the robotics mind uses these two information as input, requires the prior knowledge from the symbolic knowledge representation system to infer the answers. Therefore, the hybrid neurosymbolic reasoning model enables the robots to have cognition reasoning capability to infer answers and execute tasks by interacting with human and the dynamic world. So we define our problem as input video, which include different objects and different properties, and ask a question. For example, what are the objects X having a property Y? We require the prior knowledge from the knowledge base ontology and require the logic theory to provide the answer, such as number of objects, the names of objects which having the same property. And our main novel contribution is to build a hybrid symbolic neural reasoning model to reason complicated questions in the video through logical reasoning. Our current focus is focused on the kitchen scenario. So our model could enable the robots to answer 5 different types of reasoning. The first one, we call it the classification reasoning, such as the question, what are the non-spicy food in the video? The second one is rule-based reasoning, such as, what did you see in the video have at least 3 different tastes? The next one is explainable reasoning, such as, why is it an orange? And next one is causal reasoning, such as, what shape does the tomato change after cutting it? And counterfactual reasoning, such as, what will happen to the orange if we remove the table in the video? We use this matrix to define the reasoning question difficulties through 3 items. The first one is expressivity of query. The second one is specificity of answer. And the last one is the complication of implementation. We use the expressivity of query to define the complexity of the reasoning query, such as conjunctive query, negation query, navigational query. They require more steps of inferences. And specificity of answer is used to define how specific the answer is, such as numbers, a list of instances, and a list of classes. They are very specific answers. And answers with subsumption relationships, they are not very specific answers. And our model includes 3 components. The first component is to input a video. We call it computer vision component. We input the video into convolutional neural network, extract the visual features, such as the object names and different attributes, such as the shape and the color. We add a tracker to the video to do the deduplication to get each individual object name of each individual object in the video. The second component, we call it a natural language understanding component. And this component, we input a natural question. For example, how many fruit in the video have the same taste juicy into a BERT neural network? We do the tokenization to get each different tokens, such as how many fruit and juicy, input into an interpreter, and the interpreter helps us to convert the natural language questions into description logic queries, such as context, this X belongs to the class fruit, and this fruit has the different taste, X have juicy. We consider this one as the QX. And the third component is logic reasoning component, is our main component. This main component includes 3 parts. The first one is A box, which is defined by this visual neural network, which is the fact description about our world, which means the robot, what the robot observed in this dynamic world. The second one is called T box. T box is defined by the expert knowledge, which includes the logic theory. And our reasoner includes 3 inputs. One input is A box. The other input is the description logic queries converted and translated from the natural language questions, and the required knowledge from the ontology T-box to run the reasoning to automatically reasoning and provide the answer. For example, 3 fruit, apple and orange and lemon, they have the same taste, juicy. In conclusion, we introduce a new task. This task integrated the symbolic ontology, description logic queries, and reasoner with neural networks, including convolutional neural network and BERT. And this model could enable the agents, such as robots, to answer 5 different types of reasoning questions based on the video. And our future research opportunities could be not only hope we can apply this neural symbolic reasoning model to the cooking assistant robot. We also hope this model can be applied to other robots, such as remote doctor robot, and enable the remote doctor robot with reasoning capability, and the robot could help us to do the initial diagnosis with neural symbolic reasoning, such as what's the biggest burn area in the skin. And also we hope we can apply this model to the robots in other dangerous scenarios. So we believe today we teach robots to think, and tomorrow the robots could help us to live better. Thank you.
Thank you very much. Well, that's a wonderful message a hopeful message to live on, to end with. I'm going to ask you one quick question before we wrap up. It's wonderful to see a combination of neural and symbolic reasoning approaches there. We learn a lot often from how things fail. So does your system break in unexpected, or what unexpected ways does it break that maybe tell us something interesting?
Can you repeat your last sentence? You mean what we...
We often learn interesting things from the way that systems fail. So yeah. I wonder, does your system break in unexpected or interesting ways that that might suggest future work?
Yeah, actually, so this ontology we want to build is a dynamic ontology knowledge-based system. So it interacts with the dynamic world. So some information we might not know from the knowledge base. So we can insert this one, append this knowledge in the system, and enable the knowledge base to learn new things and uncertain things.
Great. Yeah, well, after all, the world is non-monotonic, and we shouldn't forget that. Thank you. Thank you very much. And let me express my thanks to all the speakers. I hope that you've got a nice feeling, a nice snapshot for the breadth of research in AI going on here at UNSW. I'm sorry that we couldn't welcome you in person this year. Hopefully next year we'll be on top of the pandemic, and many of you, I suspect, will be running this event again next year, and we'll have surely a physical component, and I would then be inviting you to join us for drinks in the foyer, but not this year. But next year, hopefully some of you will be able to join us, and I'm sure we'll also be putting on the event with a virtual component as well. So I've been really impressed. We've had people join us today from Europe. It was the middle of the night for most of this afternoon for them. So thank you very much for everyone attending, and have a wonderful festive break. And we look forward to catching up with many of you in the new year, hopefully in person. Take care, keep safe wherever you are.